5 days, and where we are discussing regarding the FAIR project. FAIR stands for Facility for Antiproton and Ion Research. It will be in Germany, Darmstadt, Germany, and there will be actually in FAIR there are 4 experimental pillars are there. So they are APPA, CBM, New Star, and Panda. Okay, and today in this talk, Professor Supriya Das, who is now associate professor in Bose Institute, Kolkata. So he will be talking about high energy physics experiments, science, technology, and career, where students can always participate. And he actually did his PhD from Variable Energy Cyclotron Center, Kolkata. Then he did postdoc in GSI, Germany, where actually this FAIR facility will come up. And now, presently, he is in Bose Institute. Okay, so I will request Professor Das to start.
So thank you, Soikat, and good morning, everybody. So although this is FAIR week, as he mentioned, but this lecture will not be confined into the activities of FAIR only. I think from the title you all can see that this will be a general perspective of high energy physics and how science and technology goes in these kind of experiments in hand, and what are the career opportunities here. And as he mentioned, I am from Bose Institute, and if you have any query, any question during the talk, you can stop me, or I have given my email. If you have any question specific to FAIR or other high energy physics experiments, you can write to me. Okay, so let's move on to the lecture. Now the first point I would like to make here is high energy physics experiments has a little bit 2 different ways to go. One part is which deals with the new discoveries of new particles, new elementary particles and other particles, which is classical. I would say people know about high energy physics experiment classically, but then later on nuclear physics, which deals with the reactions and structures of nuclei, and the experiments used to be done at lower energies using accelerators. They kind of come up with in the energy scale to see how this nuclear physics, nucleus and interactions of nucleus changes in the scale of energy. So this lecture will be concentrated in this activity, that is, I would say, high energy nuclear physics thing, which deals with different things than the typical high energy physics high energy particle physics. So now I think most of you, I see the age of your the entire audience. I think most of you have seen this picture somewhere or other. So this is a kind of cartoon picture which shows where the universe was created and how it evolved with time. So this is the point where universe is created, and this is called the Big Bang. It created with the Big Bang, and then this is where we are at this moment. This is about 15 billion years from the Big Bang to now. And you see the time here, and on the other way you see the energy. So that means at the Big Bang you have enormous amount of energy and almost no particles, nothing. So this is only energy. The universe was created with the Big Bang where there was only energy. And then with time going this way, and that's the start of the time. That's the start of the time and the space too. With time, where there is only energy, this is enormous energy, and the temperature of this point is enormously high. So with time it cools down, and while cooling down it creates the first set of elementary particles, the quarks and the gluons. And then for the first few microseconds, the quarks and gluons, they roam, and the photons of course, they roam around in this universe old only by microseconds freely. They are free. And then at some point, the electrons, then they come together, the quarks come together to form the the first set of particles, mesons and hadrons, and the electrons were still separate. You will see a picture somewhere where basically all these mega science projects, as we are calling them, are fitting into this picture. They are looking into the universe at different time scale, different region of this diagram. And you will see that the telescopes which looks at the sky to look for the light stops here at this point, and I mean it starts from here and stops here. So you are not able to see any light beyond this point, because at that point the nucleons and the electrons were separate. The electrons were roaming around freely and they could absorb any amount of time, and the universe is opaque at that point. So the light only starts traveling in this direction. I mean, we see the last scattering at this point. So you can only look at this universe up to this point. So beyond this, and actually whether there was a quark and gluon free state or not, that is the goal of the high energy, so-called high energy nuclear physics experiments. Okay? And in this picture, there are 2 points where there is extreme conditions. First of all, here, this is the Big Bang, at the point of the Big Bang, where there is enormous amount of energy and temperature, very high temperature. This is one extreme condition, and normal nuclear matter cannot exist at that high temperature. But at the same time, if you come here in this time also there are some astrophysical objects who inside those astrophysical objects you also see the extreme condition, but that is density. The neutron stars, you might have heard about these stars, neutron stars, and the core of the neutron star is so dense that at that density normal nuclear matter cannot exist. So at these 2 extreme conditions, you only see the quarks and gluons roaming around freely. Now the question is, to look into this kind of thing, how do you create those extreme conditions? Because we are sitting here, this is normal universe, okay? So how can we create extreme conditions? So one example is, if you take a balloon where you have air inside and you want to see the air molecules, what we will do? You have to burst that balloon, right? Then only the air molecules you can see. Otherwise you see the envelope of the balloon. So how can you do that? There are 2 ways. You can compress it, and at a limit it will burst. Or you can heat it up so that the air starts blowing up, and at that point it will go out. So that's exactly what we do. So these are the hadrons, that is the baryons and the mesons. Those are the composite particles of quarks, so they are and then it goes to, at these extreme conditions, they are liberated into the partons. They are called quarks and gluons. So these are the 2 scenarios I was discussing. So you see, these are the composite nucleons or hadrons and baryons maybe, and then you can compress them from all directions, and then at some point what will happen if you compress? These particles will come close, and then at some point these boundaries will break, and when these boundaries break, you see only quarks and gluons. Or you can start heating them up so that this boundary goes out, and then this boundaries also goes out, and then you see quarks and gluons. So the idea, the final goal is the deconfinement here. So you must have heard about the phase transition of normal matter like water. So here we are plotting the temperature and the nuclear density. The nuclear density is in the x-axis and the temperature is in the y-axis. Now you can have 2 extreme conditions where you have very high temperature but very low nuclear density. That's exactly what happened at the time of the Big Bang. You can imagine you have only energy and temperature, no matter, no particle. So that is 0 nuclear density almost. And other extreme condition is very high nuclear density but very low temperature. Okay? So these are the 2 extreme conditions, and you must have you must know about these terms like LHC. So these are the particle accelerators or facilities who are working to probe, and this is the phase boundary. So outside this phase boundary, it is free quark gluon plasma, and inside this is hadronic matter, that is confined quark and gluon. So this is the point where the early universe was there, and this is the point where the neutron stars, where you have a little bit higher density but low temperature. How to do that? As I said, little banks in the laboratory all over the world. And I will now put these laboratories, what I showed you, in this map. So you have RIC and AGS here in New York. We have SPS and LHC at CERN, Geneva. We have CIS at Germany, Darmstadt. And then the idea is accelerate the particle, bang on target, or collide them together. I mean, you take two beams and collide them. Either you have a target and bang the accelerated beam on the target, or you take two accelerated beams and allow them to collide head on. So those are the activities going on all over the world. And this is a kind of list of all accelerator facilities which has worked in this relativistic heavy ion collision, working to unravel the mysteries of the origin of universe, or how matter exists in the neutron star, etc., etc. So this is developed. I'm just reading that since 1984 now. This is 300, which is the FAIR facility, which will be operating in the FAIR facility, will now come up in 2025. So this is the timeline has been shifted a little bit. And you can see it goes to Berkeley, then it comes to Brookhaven, then it comes to Geneva, then it goes to Darmstadt, it comes to Brookhaven again, then it goes to Geneva, then it comes to FAIR. So different groups in different laboratories in the world, they are working in the similar way, but sometimes going in higher temperature, sometimes using a different nuclei, sometimes coming down to lower temperature and doing different experiments to see these things. So these are the experiments, the blue, so the black are the experiments which have been done already. Blue are the experiments which are going on at this moment. So these are going on at RIC, these are going on at LHC, and these are the experiments which will come in future, near future. So now the simple particle accelerator. I think you all know that a charged particle can be accelerated if you put high power magnets, magnets with high magnetic intensity, those are electromagnets, like this, and then if you use the oscillating electric field, then they circulate inside this, and then at some point they achieve your designed energy, and then you take out this beam, and then there is a target. So this is that simple. So you have a cyclotron, you do it. And the first cyclotron was built at Lawrence Laboratory. This is Lawrence Radiation Laboratory. After that it was named, so it is Livingstone and Ernest Lawrence. They built the first cyclotron in the world. And if you want, and you see, this is the principle and this is how it looks. It's exactly the same. I'm not saying anything which cannot be done. So, and if you want to know more about how an accelerator, a cyclotron works, you can visit Variable Energy Cyclotron Center, which is only a few kilometers from here. I would request your teachers and to arrange a trip to take you there. So, well, the more advanced or larger accelerators in the world, which we showed, they work more or less in the similar fashion. So if you understand how a cyclotron works, you will be able to understand how those more complicated accelerators work, how LHC works, or how CC is going to work. Okay? So the basic accelerator design is like this. So this is the Large Hadron Collider. I call it a modern marvel. And there is this TV show which shows modern marvels. So I call the LHC a modern marvel. And definitely, you can see this is the Franco-Swiss border. So this is a border of two countries. This is an airport. This is the Geneva airport. And this is how large LHC is, 27 kilometers of length in the perimeter. And this is the superproton synchrotron. And you see that this is the French side of the border, and this is the Swiss side of the border. And the laboratory itself, the administration of the laboratory and a large part of the laboratory sits in the Switzerland, but then LHC spans two countries. And then in this, so you see, this is the entry gate of CERN, which is in the Swiss side. And this is the LHC tunnel as it looks. Okay? So this, you can, I mean, much higher than a man height, you can walk down, you take a cycle to go there when you have to service, you have a equipment which is sitting somewhere inside the ring, and the ring is closed, then you go by a cycle and repair it and come out. So tunnel with 27 kilometer circumference passes through 2 countries, and 4 large experiments are being performed here. Collides both proton on proton and lead on lead. I always ask this question, you know why it is called Large Hadron Collider? Large Hadron Collider. You can say it like Large Hadron Collider, it's 27 kilometer, so it's large, so Large Hadron Collider. But it is Large Hadron Collider. When I say lead on lead, that's the Large Hadron. So Large Hadron Collider can collide proton on proton, which is the Hadron Collider, and Large Hadron, that is the lead on lead. So that's why it is called Large Hadron Collider. And interestingly, CERN uses all existing facilities. The PS was the first accelerator which came in CERN when CERN was built, proton synchrotron. Then came the super proton synchrotron, and then came the LHC. Okay? However, this is how the acceleration goes on. The source is here, it comes from here, and then it goes to proton synchrotron, it gains some amount of energy, then it goes to super proton synchrotron, it gains some more amount of energy, then it is injected to LHC. All existing accelerating units are used in unison to reach the energy of LHC. And interestingly, see, at SPS, you have these beam lines. So as I said, there is a synchrotron or cyclotron, and then when you achieve the energy, you take out the beam, and then put your targets here in this beam line and do experiments. So what they do is, and then PS also has some beam lines, proton synchrotron, only lower energy, and this is higher energy. So what they do is, once some amount of beam is injected in LHC, the LHC path is closed, you can continue doing experiment with SPS and PS. So these 3 accelerators work together, they work continuously. You don't stop PS or SPS to run LHC. Okay? When you stop the entire thing. So now, right now, there is 2 years shutdown going on, which will be ending in January 2020 to start new experiments. So they are upgrading the entire complex, so the entire complex is now closed. Okay? And it is not only true for CERN, Brookhaven also does that. The AGS is now a feeding line to the RIC. Okay? And GSI will also do the same thing. So these things probably you all know, but again, for the completeness, let us see. LHC is colder than outer space. The superconducting electromagnets needs to be cooled, because till now we cannot operate superconducting magnets at room temperature. We don't have superconducting magnets at room temperature. So we have to have cooling for these superconducting magnets to work. So 8.3 Tesla magnetic field, this is the magnetic field for the LHC ring. More than 100,000 times more powerful than the Earth's magnetic field. That's this number I have put only to give you the scale. This is 100,000 times more magnetic field than the Earth's magnetic field. And you can feel the Earth's magnetic field even, I mean, you just put a compass and you see the Earth's magnetic field. And this is 100,000 times more than that. And how do you achieve this? 11,000 amperes current to produce the field. Now, 11,000 amperes of current. In this room, you can only have 16 amperes, mostly. That's it. 11,000 amperes current, and that cannot be achieved without the superconducting magnets. Because for the resistance, it will all burn out, the normal resistive networks. Superconductivity comes to rescue. Niobium titanium wires are used, which are superconducting at that temperature. 1200 dipole magnets, 15 meters in length, to bend the beams. The beams are bent using these dipole magnets, and 392 quadruple magnets, each with 5 to 7 meters long, to focus those beams. So you have a charged bunch of charged particles which are similarly charged. What will happen? They will disperse from each other because of Coulomb interaction, right? So to focus them, to keep them, because you want to collide two protons, right? Two beams of protons. So unless you keep them at one place, at the tip of the needle, it's very difficult. So that is why you need the quadruple magnets to focus them. But superconductors, as I said, work only at a very low temperature. LHC magnets are cooled to minus 271 degrees C. LHC is emptier than interstellar space. You can still find something in the interstellar space, but not in the LHC beamline. Why? We cannot afford the tiny particles such as protons to hit with the gas or air inside the tube to lose their energy. We want to achieve higher and higher and higher energy, and those are protons, very small. So if they collide with air molecules, they are much heavier than that. You have oxygen, nitrogen. So proton is much smaller than that, much lighter than that. So if they collide with them, they will lose all their energy. You will never be able to achieve that. So we cannot afford this, right? With a total of 104 kilometers of piping under vacuum. So this entire beam is under vacuum. The vacuum system of the LHC is among the largest in the world. It has two parts. 50 kilometers of it, insulating vacuum with a pressure of 10 to the power minus 6 millibar. Now you have liquid helium to cool the superconducting magnets. But outside is the air temperature, right? How do you kind of separate these two? That's the vacuum. Vacuum comes there also. So the vacuum jacket, exactly the thing which you do in your thermos flask. Right? You keep hot water inside, outside air temperature is cold, and you have a vacuum jacket, right? That is exactly what is done here. And that is about 50 kilometer. 27 kilometer is the ring, so twice than that. Two rings are there. 54 kilometer, about the same, pipes under vacuum are the beam pipes carrying particles to be accelerated. And there you need to go to 10 to the power minus 10. This is 10 to the power minus 6 is okay for non-conducting jacket. But here, 10 to the power minus 10 to 10 to the power minus 11 millibar, as rarefied as on the surface of the moon, not even in the interstellar medium. LHC's vacuum system are fitted with 170 some ionization, because you have to measure, you have to keep measuring the vacuum so that it does not go up or down. So there are gauges to do that. Now we have built an accelerator. There are particles roaming around in this. And then they collide, okay? Somehow they collide. I mean, that's a big question. How you collide two protons? I mean, you don't see them, and you are driving them with electric and magnetic field, and you think that you are able to collide them, okay? It's a very, very tricky job. But, well, for this discussion, let us assume that they collide. And then what happens after that? The kinetic energies of the particles are available as heat, right? And that heat gives birth of new particles. Then now the experimental is asked, and till now the story, as I said, I am not an expert of this. That's an entirely different branch of this engineering and physics of making this accelerator and keeping it working. So now I am coming to a kind of where I understand a little bit about what you do after that. So now one needs to detect those particles and study their properties. Okay, so these particles are created after this collision, and you expect that these collisions have created the little bang, so the environment like the Big Bang, and the particles coming out of these collisions, you study them and then see whether that has really happened or not. So what do you need? You need a large number of detectors involving different technologies. It can have gas, it can be semiconductor, it can be scintillators, that's a different type of particle detector. State-of-the-art electronics to deal with very small amplitude signals. The signals which they give is very, very small amplitude, so you have to be very careful with your electronics so that you don't miss this signal with the noise you already have. So you have to have very fine electronics for this. And of course, you have millions of collisions and thousands of tracks, I mean particles are coming out, your detectors will give signal, then you have lot of data. So you have to have efficient computing for the analysis of the data. So those are the things that you need. So LHC has 4 large experiments: compact muon solenoid or CMS, a large ion collider experiment or ALICE, Atlas is one experiment, and LHCb factory, that's another experiment, that's called LHCb. And I have put these 4 at 4 positions of the LHC where they actually sit. Okay? LHC has, I should tell you that these 2 rings, you must be thinking about how they collide. 2 rings are going like this. So in one ring the beam goes clockwise, I mean if you see from top, and the other ring goes anti-clockwise. But how do they collide? They collide at points where they are like this. There are 8 points where the beams cross them. The beam pipes cross them, and then these beams collide with each other, because one going in this direction, other going in this direction. So at a certain length, the beam is actually straight, and then after that, it's like this. So at some length, they are straight. So then they collide head-on. So those are 4 points, and 4 more are still empty. So that those are kept for servicing purpose, etc., etc. So those are the 4 experiments. But you see, all experiments have kind of similarity in look. So they look all similar. Okay, so LHC looks like this. So this is 150 meter down from the surface. This is the surface. This is the Geneva Lake. This is Geneva City. And you can actually, so this is the tunnel, and there is the experiment. So you can, from these points, those are the labs on the surface. You go with a lift 150 meter down, and you reach the experimental site there. The experimental sites are there. The detectors are there. Okay. So now, why do the experiment look so complicated? As I said, I mean, all 4 experiments, they look similar. I mean, a lot of different things. Because you need different detectors to detect different particles. You want to detect photon, you want to detect neutron, you want to detect pion, you want to detect kaon, you want to detect electrons and others. You need different detectors to detect different particles. You need different detectors to detect same particles with different momentum range. So you really need lots of different detectors to detect all particles. So this is a kind of schematic of a collider experiment, okay? But the fixed target experiment also looks similar for high energy physics experiment. What is there? So there are the color code is like this. So this is inner detector, this is electromagnetic calorimeter. I will tell you what they do, hadronic calorimeter, and then the muon chamber. So electromagnetic calorimeter, they detect electrons. So what happens is, so this is the point where the interaction happens. Okay, the electron is a charged particle which goes like this, and it gives a little signal here in the inner detector, but then it deposits all its energy in the electromagnetic calorimeter. That's how the electron is detected here. Then the gamma is also detected in the electromagnetic calorimeter. It does not give any signal in the inner detector. The inner detectors are typically gaseous or silicon detectors, which are used to detect the charged particles and determine the momentum of those charged particles, and those are thinner detectors. And these are thick detectors where the particles deposit all their energy. And then the proton is identified with the hadronic calorimeter. This is an hadron. It deposits all its energy at the hadronic calorimeter part. So you see, it deposits some energy here, little bit energy there, total energy here. So that's how a proton detector, the hadronic detector works. And the neutrons are also like this. So the neutrons are uncharged particles. They don't deposit any energy here, no energy almost here. And the calorimeter and the neutron calorimeter, the hadronic calorimeter, they deposit all their energy, because this is uncharged particle, this is charged particle, so they interact with the inner detectors too. Then you have the muon chambers, which almost does not interact with any of them, but interacts a little bit here. Okay, you still have one more particle left which does not deposit any energy or interact anywhere in this entire thing, and that is, who is this white guy who is fugitive? Neutrino. They don't interact with any of them, and that's how they go out. Okay? So those are the neutrinos. So now you know why they are complicated. So this is the picture of a large ion collider experiment, or ALICE, and you see these two are one gentleman and one woman, and you can see the scale. You can imagine the scale of this detector. So this is the point where the interaction happens, and you have detectors wrapping around the entire thing like this, and you have lot of different detectors, and I have written what it does: the high momentum particle ID, time of flight, transition radiation, which does the electron ID, photon multiplicity detector, time projection chamber for the tracking and energy deposition, inner tracking system, forward multiplicity detector, and other detectors. Okay, so as I said, different detectors are used for different. These two detectors are marked with blue because they have special significance. This is a detector which measures the number of photons, counts the number of photons at the forward direction. We call forward direction at the direction of the collision, the beam directions. And the central direction is like this. So they are forward and they are central. And for a fixed target, this is forward and this is backward. This is forward. If this is a target, this forward direction is this and this is backward. But for collider, both are forward direction because you don't know, there is no target. And this is a detector which detects muons. Okay? So this detects photons and this detects muons. These two detectors, this detector is entirely built in India. And part of this detector, significant part of this detector is also built in India. That's why I tried to kind of emphasize that India is important in this experiment too. So it's all about teamwork. So these experiments are a teamwork. No one, so like these accelerators are not built in one country. This is all collaborative effort. You don't have resource, financial resource and intellectual resource in one country to build those things. Similarly, these experiments are also collaborative effort where you have different detectors and different countries, different groups, they make different detectors, they build different detectors. And so when you take the data from all detectors from different angle, then only you can see the picture. It's like this looking at an elephant, right? So 1,000 scientists from all over the world are working to build, operate and extract scientific results from ALICE. In total, 7,000 in all 4 experiments. So this is really a very big teamwork. So this, I just showed a little snapshot from all experiments, like at 2 GeV you have this many particles, at 2 GeV, again at 2 GeV you have, these are different detector setups. 200 GeV you have little more number of particles, 150 GeV, see energy is going up. When you reach 200 GeV center of mass energy, see this is beam energy and these are fixed targets. So actually you can calculate what is the energy available at the center of mass. This is much less, right? But this experiment is 200 GeV center of mass, much higher than all these. And you see the jungle. This is the jungle of particles. You have to detect every one of them with precision measurement, precise measurement of momentum and etc. Then only you can get the physics out of it. And when you reach to ALICE or LHC, the jungle even gets deeper. Okay? Your path is even tougher to identify each one of them. So that's the complicacy and challenge in these kind of experiments. And then those many tracks, so much of data. This is a pile of CDs you can make in 1 year of LHC data. And you can see a Concorde flying over there. Right? How do you deal with this? No one computing farm sitting at one place can handle this. And that's why we have a grid. Like the electricity, this is data grid. So this is the place, so the density is only because Europe there are lot more collaborating institutes, scientists working there, and there are other places too, those who are connected with this. How does it work? It works like, so there is a name, Worldwide LHC Computing Grid, WLCG. It has 42 countries participating, 172 computing centers, 170 computing centers. 2 million tasks run every day. By task I mean one analysis program. One task is one analysis program, which is analyzing the data. 2 million of those tasks run every day. 750,000 computing cores. By now, all of you know what is a computing core. A computer has 3 core, 4 core, 5, 6 core, 8 core like this. So 750,000 computing cores are working 24 hours to do this. 400 petabytes of data on disk and 400 petabytes on tape. So forget about it. And we also have one such computing center. When I said this 172 computing center at VECC Kolkata, and India has one more at Tata Institute of Fundamental Research, TIFR Mumbai. This is for the ALICE experiment, the other one is for the CMS experiment. And how it is actually like a cobweb. So you have tier 0, which is at the center. This one is the tier 0, that is the CERN data center, and another one is Budapest. So you all know that if I keep my entire data in one computer, if it crashes, I'll lose everything. So that is why it is mirrored with Budapest. So this is two exactly same copy of data kept in two tier 0 centers. Then around this, there are two tier 1 centers, 14 centers worldwide. And then around them are tier 2, 160 centers across the globe. The centers at TIFR and VECC are these tier 2 centers. And the tier 3 is the computing cluster at your institute or your on your table, which is connected to this. So how it works is you write an analysis code and submit it. You don't care where it is running. So it can be running in somewhere in America or Europe or somewhere. You don't care. So it just takes it. There is a management node. There is a management network which decides, which sees which core is sitting empty, sitting idle, and then it directs the task there, and that's how it goes. This whole endeavor started in 1991 with a small small experiment, WA93. This WA and NA, those are nomenclatures as West area and North area at CERN. And then it came through long time, and now we are planning for 2025 the CBM experiment at FAIR Darmstadt. So that's how the Indian groups are involved. So those are the India groups, and lots of new groups have also joined in the endeavor. Now, as we are talking in the FAIR week, let's see what is facility for antiproton and ion research. This is a fantastic example of Make in India, because I would start this discussion on FAIR showing you three things. That is the beam stopper, there is a power converter, vacuum chamber, and superconducting magnets, which we are going to build and supply there, which will be sitting there in the FAIR accelerator running the FAIR. So that's a fantastic example. And when we did our PhD, everywhere we went, and we saw the electronic modules and everything coming from outside, from Italy, from USA. And now you will go to FAIR and you will see this box sitting there, made in India. ECIL, Electronic Corporation of India Limited, has got a contract of making 600 of those, which will actually run FAIR. And 67 of them, the first batch of them has already been delivered. They are sitting there. The FAIR is being built, and they will be sitting there. So that's a very nice achievement after so much of work for so many years by so many people. So now we are building the accelerator. And this is also being designed here. This is also, right now, this is being built in Bangalore by one of the companies, and the first kind of prototypes are ready. They will be tested at FAIR, and they will give us the green light to go for mass production. Okay, this is a success story. What is this? What is FAIR? What is FAIR? This is what is FAIR. This is how, like you had a ring in CERN and LHC, etc. So FAIR facility will be like this. So this is the existing facility at GSI. This is the CIS-18, this is heavy ion synchrotron, schwer ionen synchrotron in German. Heavy ion synchrotron 18 is 18 Tesla, by 18 it means 18 Tesla meter, that is the bending power of the magnet. And we will build CIS-100 and CIS-300. So the magnetic bending power will go up by scales. But still it will be used as it is used in CERN. So this is the beam line, this is the beam where it originates, it comes to the cis 18, it goes to cis 300 and then it comes to, and here again these will be fixed target experiments, not in collider mode. And this is the experiment which is the compressed baryonic matter, which will again study this core of neutron star. This is called compressed baryonic matter, the name suggests that. We will compress the baryonic matter and see how it behaves. And the other things are for different experiments. This is a multi-purpose facility. FAIR is a so the LHC is practically particle physics and nuclear physics and high energy nuclear physics. But here it is not like that. So there are four pillars, four experimental four major experimental activities. One is CBM that kind of deals with this high energy nuclear physics, where we will look at the core of the neutron star. The next is new star, that is the nuclear astrophysics and nuclear reaction and astrophysics. The last talk in this morning, first talk of this morning was on this. So this is the super fragment separating machine, fragment separator, which is sitting here. I have just blown up this area, and there will be fixed target experiments doing nuclear physics at this energy, okay, and at lower energies, because the energy of this will be much lower than LHC. Why we going to the lower energy, we can discuss at the end. Then there is PANDA, which is proton antiproton annihilation at Darmstadt. Proton antiproton annihilation. So there will be beam of proton and beam of antiproton round revolving in this ring, and then they come to collision and they annihilate. And Darmstadt is the name of the city, so that is the name of the experiment. This experiment looks at the hadron structure. What is the structure of hadron? How spin of nucleons, spin of quarks affect the spin of nucleons, etc., etc. That's the goal of the PANDA experiment. And then there is another group of experiments that is APA, that is applications of plasma physics and atomic physics. So this is a multi-purpose facility, as I said. So the coming up is the compressed baryonic matter experiment at FAIR in Darmstadt 2025, as I said. We have seen QGP at CERN, but then what is the equation of state at high baryon densities? QGP is quark-gluon plasma. What is the order of phase transition? We say that the phase transition happens. The phase from confined nucleon to deconfined quarks and gluons, there is a phase transition. But what is the order of the phase transition? Where is the critical endpoint? If it is a first order phase transition, and if we see at LHC or RIC a crossover, then where does this first order phase transition ends? That is the critical point. Where is the critical point? Those are the questions that will be addressed at CBM. And how? So this is, as I said, this is an artist's impression. This is the current facility, and this is how the facility will come up in this. This was a forest a few years back. So trees have been cut, and this is will be a multi-purpose facility working in nuclear atomic particle physics experiment and with a very high intensity beam. And the current status, this is October 2019, is this. They have started cutting the tunnel. The tunnel is already, some part of the tunnel. You see the existing facility here. So this is the existing GSI, and this will be the CIS 100 and 300 ring. The construction is going in full swing to meet the deadline to start the beams in 2025. The existing CIS is here, and the beam will be transferred to this through this line, through this point. Okay, and why are we discussing? Why are we in this exhibition here? Because again, India is one of the founding countries of FAIR. There is only 9 countries. You can see the flags here, and India is one of them. And India will contribute to 3% of the entire cost of building the FAIR and doing the experiment. Okay, so what is the physics case? What are we going to do in CBM? So you see, this is a neutron star. I will not go into details of this. This will be a little bit difficult for them. If you ask, I can answer your questions. But For the time being, this is a neutron star, and if you go, this is the outer crust, this is the quark matter, but then if you go to inside, this inner core, this is very, very dense, as I said, and our expectation is inside this, there is only quarks and gluons roaming freely. There is no confined matter in this. But how do you see this? You see this through many things. You see, we had a lot of fanfare about this Higgs discovery at CERN. We all know CERN because of the Higgs. And we all talk that Higgs is the reason for origin of mass. But do you know Higgs is the reason for origin of mass for only 5% of the mass? Less than that. The rest comes from the QCD mass, how the quarks interact inside the nucleons. So Higgs is not the end of the story. So what we are going to see, so this is, you see, this is the Higgs mass, okay? And for charm bottom and top, all mass is given by Higgs mechanism. But we are not charm bottom top. We are UD, that is the normal nuclear matter, neutrons and protons. So here you see, for U, it is less than 3% of mass which comes from Higgs mechanism, but the rest comes from QCD mechanism. And how do you probe that? You probe that this in medium modification of hadrons, and that will be done at FAIR CBM experiment. So these are some short-lived particles, rho omega phi, who decays into electron and positron or mu plus and mu minus. CBM experiment will put their detector to detect these mu plus, mu minus and electron positron, to go back and reconstruct rho omega phi, look at their mass, how this mass, what is their mass in vacuum and what is their mass in the high density environment, to see what happens actually for this mass generation. New phases of strongly interacting matter, okay, I don't want to discuss this, but anyway, if you ask, I can still see. So here in this Indian contribution, I will focus on this in medium modification of hadron. As I said, that we will detect the mu plus and mu minus. So this is how a CBM experiment looks. This is not the real experiment, it's being built. So this is only simulated picture. So the target of CBM experiment sits somewhere here. This is the blue thing is a magnet, dipole magnet. The target sits here. The beam comes from this point. Then there is ring imaging Cherenkov counter, and inside this magnet there is the silicon tracking stations. Well, let me tell you one thing. Otherwise, you will be completely you will not understand what it is. So when the collision or this beam hits on the target, the charged particles come out. So now if you want to know the momentum of the charged particle, how do you know the momentum of the charged particle? What is the method? The method is you apply magnetic field, then the charged particle will bend in the magnetic field. If you know the magnetic field, you know the momentum, right? So that's the principle of particle identification in high energy and nuclear physics experiment. That's why there is a magnet. There is a magnet in Alice, there is a magnet in CBM, same thing. But in Alice, only the tracking equipment was time projection chamber. Here it is silicon tracking station. So silicon tracking stations are sitting inside this magnet. After that, there is this ring imaging Cherenkov counter which detects the electrons and other detectors which detects other particles. Interesting is, this is what you see here is a mu1 detector. So the real estate of this experiment do not allow us to do the electron and muon measurement at the same time. So we cannot do that. So what we do is one after the other. So for a certain amount of time of the run, the ring imaging Cherenkov counter will be there. After that, they will be pushed away this side, and the muon will go and take their place, muon detector. So this is the muon detector. And how a muon can be detected? As I showed, if you put everything, if it pierces everything and comes out, that's a muon. All other particles will be stopped. That's the simplest mechanism of detecting a muon. You put lot of things in front. So all other hadrons, all other charged particles will be absorbed by them. Muon will come out because muon interacts very less. And that's why these thick absorbers are there. And this is This muon detector will entirely be built in India. Once again, the entire detector will be built in India, which will play a very crucial role in the physics program of the CBM experiment. And how are we building the muon detectors? Using a very different technique, because you have lot of particles, you want to detect them, and most importantly at CBM you have a very high intensity beam. That means number of collisions per second is much more. So you have lot of particles and you have lot of interactions. So particles are falling on your detector very fast. So your detector has to respond very fast. So that's the reason why we have chosen this different technology. As I said, different detectors uses different technologies to detect different particles. This is a gas electron multiplier. This is little bit technical, but I can stop if you do not want to listen. See, the idea is for any detector, you have a particle going through the detection material. The particle interacts with the material, keeps some energy, you get some energy, you detect that energy and detect the particle. That is the idea. Now a charged particle going into the gas ionizes the gas. Okay? But so if you take a volume of this and if a charged particle goes this, only tens of electron and ion will be generated. If you take 10 electrons, it will not be able to produce any signal. 10 electron charge is how much? Your noise will be much higher than that. So you have to multiply them, right? And that is why you use 2 electrodes to pull them very fast so that they get enough kinetic energy to ionize more gases. So those are secondary ionization, and then at the end you get lots of electrons. That's the signal, and that is a typical gas electron principle, gas detector principle. Here the same principle is applied, but in a different way. What is the different way? See, this is a polyimide or plastic film, okay, and on top and bottom there is copper cladding of 5 micron. So the plastic thickness is 50 micron and the copper thickness is 5 micron, and you have holes of 70 micron diameter and 140 micron pitch. The center to center distance is 140 micron. And you apply voltage on this and this. What will happen? If you apply 300 volt typically on between this and this with a 70 micron diameter hole, what will be the field inside this? Tens of kilovolt per centimeter. Tens of kilovolt per centimeter, which is enough to produce this secondary avalanche, right? So what happens is, you see this, so your charged particle has gone through this medium. So this is your entire thing, and then there is a ionization. From ionization you get an electron. So this electron is now coming down. Okay, it goes into a hole, it produces tens of electrons exactly like this. Then it goes into another hole, another stage of multiplication, and this is how it works. So you have one gem here, you get so many electrons, and if you want to increase your gain, you put just another foil and get enough gain to use the signal. What is the fun here? Why we are using this? The fun is, you see, the position resolution is very high. Here, by position resolution I mean 2 tracks, if they are very close, you can identify 2 tracks. You see this pitch of these holes and etc. So you don't see them in blind eye, I mean naked eye. So you have to see through the high power microscope. This is taken from microscope. So this is one thing, and this detector is very fast response. This has very fast response, okay, and that is why we have chosen this. So this is, we are doing some R&D, and I can skip this. So this detector is, we are testing. This is the efficiency with voltage. This is the spectra of the energy. So energy deposition in this detector takes this shape, and the efficiency, if you increase the voltage across these 2 plates, the efficiency goes up and then reaches about more than 90%. Efficiency means you shoot 10 particles, how many you detect. If you detect 9 of them, then it is 90%. So that's what it is. So you increase the voltage. So initially if your voltage is too low, then it does not produce this avalanche, so you don't detect some of them. And if you reach here, you have 100%, almost 100% efficient. That's how. So we are showing this to show that this detector is working. The purpose of showing this is the detector is working. And you see, if you change your energy of the particle, your spectrum is changing towards this side. So the detector is working. If the detector is working, we have to make larger detectors because this is very large. The actual detector is very large. So that's what is being done here. You see, this is a gem foil. The foil which I showed there with a microscopic view, this is a real view. This is the real size view. And people are cutting this foil into a trapezoidal shape because if you have to make a detector which is circular with discrete modules, this is the best shape possible, right? So that you don't lose any area between two modules. And you don't make a one large detector like this, you cannot handle it. So you make modular detectors, and if you have to encompass a circular disc, then trapezoid is the best shape, right? That's why we are making it a trapezoid. So now the detector is cut in proper shape and put it here, and you know this, right? What is this green board? Printed circuit board. So what you see in all electronic equipments. That's what is the printed circuit board that will go on top of this detector, and the electronic boards will come up here. That's how it works. Yeah, so the idea is you have to detect a particle, right? So a particle, charged particle going through a gas. What will happen? If it has enough energy, more than the ionizing potential of the gas, it will ionize the gas and it will create ions and electrons. So you can have, how will you register that there is a particle? You have to have a signal, right? And this is the easiest way to have a signal. If you have electron, then you can attach, you can put two electrodes and you will get the electron. And if you get an electron, if your electrode was not giving a signal before, then if there is an electron comes onto your electrode, it will give a signal, right? You will see the drop in voltage. That's the drop in voltage. So now 1 electron or 10 electron will not be able to show you that much drop which you can detect. So that is why you allow the secondary ionization or secondary avalanche creation, which creates lots of electrons, which you then arrest at the electrode and get the signal. Does that answer your question?
It makes the detection easier, but how does that give us information about the momentum change?
Oh, good question. The particle, so the amount of energy deposited in the gas will be depending on the amount of energy the particle has, right? So from there you can go there. So if it deposits more energy, you will get a larger signal. So that's it. I can answer your question a little bit more elaborate way. Let me just finish this. I will come back to you. So that is how a detector is being built. As I discussed, the accelerator is built, the detector is built, the experiment is done. And then at the end you will get physics results. I am not going into details of the physics results because I feel that will be little beyond your understanding at this moment, but I tried to kind of give you the flavor of the physics which we are doing. So you get the particles, you detect the momentums, and then from there you kind of correlate and go to the physics. But then I will show you how you can come here to work with us. This experiment, for example, especially CBM, is going to be operative in 2025. So in 2025, and we are, of course, we are working, we are building detectors. But when the experiment comes up, we need you, right? So there are two paths, and I think Mr. Rai will be better knowing this, but still, for the completeness of this discussion, there are two ways you can contribute, you can come and join us. That is, if you study general science, you get your master's degree from any university in India, ISAR or NISARS. Then clear some of these national level exams, which makes you to avail the fellowship. NET makes you avail the fellowship, and the INSPIRE also. Then join any of these collaborating research institutes, universities, IITs for doctoral research who are working in this field. Or many of you will be engineers you get your BA, BE or BTech degree, you come to, these are two places where the engineers get to do science, BARC and the CAT, which is in Indore, Center for Advanced Technology. You join there and directly you will be part of these kind of experiments. Or you can do your MSc and directly join BRC. You can be either MSc in general science or you can be BTech in engineering, you can join BRC or CAT. Or you can get to your BE or BTech degree and come to join any of these collaborating institutes and join this research. And for those who are thinking that I need some support, of course financial supports are there through this National Talent Search or Jagadish Bose Talent Search or KBPY or Inspire Fellowships, which supports the people who are working in general science as a student. And we have 37 PhDs done in Alice India collaboration since 2007 only. So we started counting since 2007, and we already have 37 PhDs done. Some of them have already got jobs, some of them are in abroad doing their higher studies.
We are not doing
And
that
already
job.
5 in the CBM India collaboration. And there is of course a lot of fun in doing high energy physics. You go to different places in the world, you enjoy, right? So let's summarize what we discussed. Science and technology works hand in hand in experiments in high energy physics. State-of-the-art technology in all branches are in use in this area. Opportunities for young engineers even to work in a global field. And India has come a long way and looking into future, looking into you for more opportunities. And believe me, this is fun. This is CERN ski club. You can go to CERN and join a ski club there. Or you can sit on one of the dipoles and take your picture. Okay? Thank you very much for your patience. I can answer your question in a more elaborate way now. So, yeah. Sure. Please.
Actually, yeah, it's on. Actually, my question is the FAIR project using the same kind of accelerating technology that was in CERN? So
Technology is the same.
It is the same.
Yeah.
So what is the next level that FAIR is going to achieve?
That's what I say. That's what I. So there was this phase diagram. X-axis was the density and the y-axis was the temperature, right? So at RIC and we were probing the high temperature, low density region where the early universe was there. Okay, we are almost there. Okay. Now we are coming down to this. So here what we need is not very high energy. So high energy collisions give us high temperature. And when the very high energy protons are there or lead ions are there, what happens is if you have velocities about light, it's almost 9.999969 after the C, then you have spherical nuclei. They don't stay spherical, right? They become flat because of Lorentz contraction. And then when they pass through, the nucleons inside, they don't collide them actually. So they interact them through their force fields. So practically in this region, so when these two pancakes pass, in this region there is no matter. It's only energy. So that's a transparent region, okay? So at this high energy. So that is why we are saying that this is creating the early universe scenario where there was no energy, no matter, only energy. Here we are coming down to this regime, okay? Here what we want is not this way, but the other way is the stopping. Two nuclei are coming and stopping together to create this very high density. Okay, and there we want to go to lower energy. So the high energy CERN accelerator cannot go this way. So it can only go to that way. If you make higher energy accelerator, you will only go a little bit more closer to the temperature axis. And you cannot. So here the goal is not high energy, but low energy, high intensity, because this in medium modification and etc. Those are very rare probes. they happen, the Jep psi is produced 1 in a million event. So you want to create millions of data, millions of collision, so that you get those rare events probed. That is the idea of high intensity, low energy accelerator.
So, sir, my question is that all the particles in the LHC are moving with a very high velocity and approximately about the speed of light. Then why the theory of relativity is not taken into account here?
Who said the theory of relativity is not taken into account? It is taken into account.
So, sir, how can we explain the time dilation here?
That's what I said. In LHC, you take two beams of lead, right? Now, how does a lead nucleus look like in normal? It's a sphere, right? So when you take them at this high energy, they are not sphere. They become flat, like a chapati. Okay? So these two chapatis then collide. They become like chapatis because of relativity, because of Lorentz contraction.
And, sir, how can we explain the length contraction factor?
That's what it is, right?
So then
A sphere becomes flat because of length contraction.
Oh, thanks, sir.
You will definitely get higher energy for a smaller circular accelerator compared to a much larger linear accelerator. So now you can think of which is more efficient. And at the same time, as we said, going from fixed target to collider, this is another question. Going from fixed target to collider is also, there is a reason. Why do you go to collider? Because if your target is fixed and the beam is coming with the beam energy, see, for the production of these particles, you need to have energy available at the center of mass, right? Think of your mechanics knowledge. So there is a target which is fixed, the beam is coming. So you start from this point. Where is the center of mass? Here. You come here. Where is the center of mass? The center of mass is now moving. Okay? So you lose the energy moving the center of mass. Right? Now you take a collider. You take two beams. They are coming. Where is the center of mass? At the center. They come here. Where is the center of mass? At the center. You don't lose any energy at the center of mass. The entire energy of these two beams is available at the center of mass. So that's why people went from fixed target to collider.
Any more questions? So let's thank Professor Dash once again. Then we will start the formal quiz. So we will start asking questions to you. Okay?
Are you ready for the quiz? Can you hear me? Okay, so are you ready for the quiz? Can you say it louder? Ready? Okay, so let's start. So I'll start with a very easy question in the beginning, and then some tricky questions will come on the way. So the first question is, how many types of quarks are there?
You just raise your hand, then we will come to you.
Yes, you'll raise your hand and then, okay, see one hand over there.
6 types: up, down, charm, strange, top, bottom.
Wow, very good. Congrats, come.
So I will request Professor Dash to hand over the prize. First, you introduce yourself.
Hello, I am Ritam from South Point, class 11. I am Ritam from South Point, class 11th grade.
Thank you.
Okay, so the next question, it's regarding networking. So what is the full form of GPS? Okay, at the end. Global Positioning System, that's exactly. And how does it work? I mean, what's the principle of the GPS?
Okay, it's a global positioning system.
Yes, yes. And the
There are
principle?
satellites, so they provide the networks, and from there.
Okay,
I can't
and
explain
can
that.
anyone else say what is the principle of, or what mathematical principle is involved in the technique of GPS?
So essentially, there's a network of 24 satellites geostationary satellites over the planet. So whenever a device wants to know its location, it contacts sufficient satellites to they measure the time difference between the
Yes.
like
That's
they
a
take
method,
two
but,
timestamps, so they can figure out the distance from the time because they know how fast the information is traveling.
So minimum how many satellites do you
So
need?
you will need 3 spheres to detect and 4 to actually detect with guarantee, like better precision.
Yes.
So 3 spheres, 2 spheres intersect in a
Yes.
circle.
Yes.
The third sphere will intersect it at that circle at 2 points.
2 points.
And the fourth one will find its location
Yeah.
uniquely.
Exactly. You're right.
So you tell your name.
Hi, I'm Pritha from South Point Class 11.
Hello, you already know me.
Okay, so again I will request Professor Das. This is for Pritha. Yes. And this is for.
So come on, KV, why are you people sitting so quietly? Next question will be for this part. You have to answer. So with using which telescope was the image of black hole captured recently?
Event horizon.
You were supposed to raise your hand.
I think it's Hubble telescope.
No.
Event horizon telescope.
Yes, that's right. That's right.
Yes,
Come
good.
on. And does anyone know it was which black hole? I mean, in which galaxy was that black hole? There is another name. Actually it's called the M87. So it's not Andromeda.
So my name is Chandraprakash Singh and I am from KB Bagpur Air Force.
Next question is, suppose you are holding a torch and light is coming out. You know the velocity of light, right? Say it's c. And now you are running in the direction of the propagation of the light at a velocity v. So the question is, there's a question.
First you ask the question. First you ask the question, then you answer.
From the ground frame, what will be the velocity of light?
Was it the question?
What will be the velocity of the light with respect to an observer who is stationary?
C.
C.
Why?
Why?
Because it has the same velocity in all frames. From that only we got the relativistic transformations and all.
Okay, you come.
Come.
I'm Shamanay from South Point High School.
So the next question, why are you not raising up your hand and you're saying galat baat hai? So the next question is, in a micro oven, why does the food gets heated and not the container?
Because molecules of water get heated
Yes, how?
due to radiation.
Okay, so the microwave radiation rotates the water molecule. I see, you're absolutely right. So you come up, you got the right answer. So food having water molecules will get heated up only, and the containers do not have water molecules. Very good. So introduce yourself first.
I'm Aniket Banerjee from KVS Barakpur.
Class?
11.
Okay. Okay. I want to ask a basic question. What are the fundamental forces in our nature?
Yeah.
And
The gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force.
okay. And what are the carriers?
Mediators.
Mediators.
Someone else?
And which one is strongest and which one is weakest?
Mediators. Who will tell the mediators? Mediators नहीं पता है. पढ़ाई करते हो तुम लोग.
What are the mediators?
कैपिटेशन का क्या है? Mediator. जो force को
All
mediate करता
interaction needs some mediator for the interaction. What are the interaction?
है. ज्यादा टोन से बोलते हैं उसको.
মিডিয়েটর গুলো ইয়ে তোমার ইলেকট্রোম্যাগনেটিক ফোর্সের জন্য ফোটন ডাব্লু আর জেড বোজন যেটা স্ট্রং আর উইক নিউক্লিয়ার ফোর্সের জন্য আর গ্র্যাভিটির জন্য
স্ট্রং এর জন্য ডাব্লিউ এন্ড জেড বোসন নয়
উইক নিয়ন না গ্লুঅন রাইট
लोगों को तो बहुत कुछ पता है यार, बहुत एक्सपर्ट हो.
আর গ্র্যাভিটির জন্য গ্র্যাভিটন
मुझे नहीं पता.
ওকে কাম Come. You will get a fair badge.
Shivam is also right.
You will also get.
You will also,
Come.
yeah, of course.
You introduce yourself first.
I am Shivam Kumar of class 11th and I am a student of KV Barakpur Air Force.
I am Soumya Das from class 11 from South Point High School.
I request you give 2 batches to them.
Teacher photo.
So question is, you have two things. One is 100 degree centigrade water, and another thing is 100 degree centigrade steam. So which one is more hotter? And why? And why?
Hundred degree Celsius steam, and because of latent heat of vaporization.
How much energy?
How much energy?
हाँ ऐसे ही
540 calorie.
यही ट्रिक है नहीं ये ट्रिक है ऐसे ही होता है.
Yes.
Yes, you get the point. আটা করছি.
You identify the person, okay? I am the first Indian director of Indian Institute of Science, Bangalore. The British established this institute, and they were all not Indian. So he was the first Indian director of IISc.
I am Orko Roy from South Point High School, class 11.
Do you all know the constituent of an atom? What are they? Yes? Proton, neutron, and electron. And of them, which one is elementary? Yes? Electron. Nobody will get prize.
Okay.
Because you have to raise your hand. Okay?
That's the problem.
Yeah. Next.
So I'll ask another question. So all of you have seen the dish TVs hanging at the rooftop of the buildings, right? Tata Sky dish TVs. So in which direction do they point? East, west, north, south? And it's a twofold question. So the next question will come after it.
At the current location of the satellite which is transmitting the signal to...
So which way is this satellite?
It can be in any side in a specific part of the sky.
Can be in any side? No.
West.
No. So there are only 3 options left.
East.
No, one more option. So there are only 2 options left, and now you have to give the correct answer with the explanation.
So I think it points at a satellite, and the satellite should be geostationary. So it should be near the equator, which means it should be towards the south.
Exactly, you have the right answer. Excellent.
That's why I'm Ritam.
Next one will be.
So you have heard the talk on fair. So what are the 4 pillars of fair? What are the 4 experiments which will be performed in fair? Can you tell any of the 2? 2. Wait. 2.
Appa and panda.
And other 2?
CBM and New Star.
2 fair batches to them. Or we can give 1 bag, you can.
My name is Swastika Ghosh. I'm from Kendriya Vidyalaya, Bairpur Air Force, class 11.
My name is Shoshi Roy. I am from class 11 and from Kendriya Vidyalaya, Bairpur Air Force.
So, my question is that all of you know that lakes freeze in cold conditions in winter. So, what will be the temperature of water under the 4 degrees Celsius? Right.
Are you sure?
Right.
I am Shahindas Bairagi of class 11th and I am from Kendriya Vidyalaya, Barakpur Air Force.
Okay, so next question. Listen carefully. If you light a candle at space, Suppose you could do that. What will be the shape of the flame?
And why?
Yes, and then why? Of course.
Maybe it's circular as because there is no gravitational force or something like that.
Yes, you answered it correctly. The shape will be spherical, but the explanation, can you means why?
Means
Then gravity will pull down the flame in here and right. Yes. So,
I don't know. I'm sorry.
so what happens? Hot air from the bottom rises up. So it's the convection currents that blows up and gives it a shape like this. And due to the gravity, this thing is happening, right? Because of the convection current. And in space, there won't be this convection currents. Okay, so you get the prize. Come on.
I am Anurag Das from class 11 of Kendra Vidyalaya, Barakpur Air Force.
Now, suppose you have 4 type of materials like rubber, 1, 2 plastic, 3 clay, and 1 is steel. Okay. Now you have to tell of them which one is more elastic.
Now last question. Last question. Who is he?
Okay.
Scientist. Good. Right. You get the prize.
It's very simple, actually.
Just raise your hand. Okay.
2 eyes, 1 nose.
Wow, what an observation.
Richard Feynman.
No. You can guess actually. Yeah.
J.J. Thomson. J.J. Thomson.
James Chadwick.
James Chadwick. Yes, right. James Chadwick. Come.
तुमको मिला है ना?
Come. Both come.
My name is Anshika. I am from class 11 from Air Force Barakpur.
What did he discuss?
Sorry, sir, protons. No, sir, neutrons, sorry.
I am Abhijit Bhaduri from South Point High School, class 11.
हाँ, तुमको भी तो मिलेगा ना? कुछ नहीं. अच्छा. हाँ. अच्छा बताओ quantum teleportation किसने?
Okay. So this was the last question of today's quiz. So thank you all for coming and listening the talk and participation in the quiz. Thank you.